Hello, this is the TA Chris doing round 2 of a run through of exam number 4. Uh, I've already did this earlier, but when I was looking over the videos, there was some issues, and so I apologize for the lateness of this, but I'm doing it all again. A run through of exam 4A as an example for what you're going to be doing for Friday. And I'm just going to run into it right now so that hopefully I can get this uploaded soon for anyone who wants to watch it tonight. So I've noticed there's a problem sometimes with that, but I'm just going to enter my name. And we will get started. So our first question here, the discovery of the structure of DNA was published by Watson and Crick. What was the name of the exceptional scientist who performed X-ray diffraction studies? And really, this is just something that you'll need to memorize and should memorize because Watson and Crick did not really give due credit to the contribution of Rosalind Franklin. And it was that's a name that you probably need to remember for the amazing contributions that she made. Aretha Franklin will not give you any credit, unfortunately, so be sure to remember the first name as well as the last name. Then we have, what are the 3 forms of kinetic energy that molecules possess? And this just gets down into the basics of how molecules are actually behaving. And a good way to visualize this, I think, is to imagine just like a diatom of 2 molecules linked together, bonded together. Sorry, 2 atoms bonded together. There's various, kinetic energy just means movement, basically. So you can have rotational movement where a molecule is spinning around. You can have translational where the molecule is moving. Like a lot of the energy in air is translational energy of how quickly it's moving around in whatever container that it's in. And also bonds, unlike the molecular models that you sometimes see, are not stiff and unyielding. There is a constant motion in and out of bonds lengthening and shortening. They're sort of vibrating back and forth. There is an ideal distance, but there's energy that will move them back and forth between that ideal distance. So vibration is the 3rd form of kinetic energy. So all of these together will lead to the total kinetic energy of a set. And now we've got some formatting issues because I converted this from a PDF to a Word file to do this. We need to name 3 factors that affect the rate of a chemical reaction. And I'll just briefly, because this will come up again, a big aspect of chemical reactions is going to be the energy requirements for the midpoint. And so that's mainly temperature. And you've seen if you were in the lab section, that when we heat certain beakers up with reactants in them, it sped up the rate of reaction. Another important thing is the concentration, because a lot of times reactions are taking place in water or a gas that's part of a larger gas mass, and how much concentration there is means that they determines how quickly these molecules will interact with each other properly. And of course, just the physical state. Like a solid is not going to react nearly as quickly as a liquid, and a gas is going to react even faster than a liquid. So the state of the matter. And sorry about that. So when we talk about state, we're meaning, solids, liquids, and gases. Also, a catalyst is a possible answer for that because of what catalysts are able to do. And so then question 4, how does the magnitude of the activation energy affect the rate of the chemical reaction? Well, just there's a good reason that I put this up, because temperature is capable of giving molecules enough energy that they can get over that barrier. That's what can slow a lot of reactions down. And so what you got to keep in mind is that the higher the higher the activation energy, the slower the reaction will be. You have a lot of extremely spontaneous and extremely energetic reactions that you don't see every day because the activation energy is so huge. There's a reaction called thermite, which creates so much heat that it will produce liquid molten iron. But its activation energy is so high that you need some specialized equipment to get that sort of reaction started. So the higher the activation energy, the slower the reaction is going to be. Then we have here number 5, adding the correct catalyst to a reaction vessel will increase the rate of the chemical reaction. Explain how adding a catalyst will increase the rate of an endothermic reaction in respect to the pathway of the reaction and the activation energy. So these are the two things that you need to talk about. And so the fact that it's endothermic is actually kind of a red herring here, because whether it was an endothermic or an exothermic reaction, catalysts are all about increasing the speed. And the way they do that is by changing the pathway and changing the activation energy. So a catalyst creates a new pathway or new reaction pathways. That reduce the activation energy. And as we saw, the higher the activation energy, the slower, and so therefore the lower the activation energy, the faster the reaction can take place. And now we hear, according to the kinetic molecular theory, increasing the concentration of the reactants will typically result in a reaction proceeding more rapidly because, and really this is just a matter of, there are 3 specific conditions that have to take place for a reaction to happen between 2 molecules. You know, you've got some molecular structure here with something or other, and then some molecular structure over here. In fact, let's think. I can visualize it with the esterization that you all did in the lab section and had a question on. Sorry. So you've got an alcohol and a carboxylic acid here. You know, just R is the way that we usually talk about, you know, there's something else going on here, but all we care about here is the OH. So the first thing that obviously has to happen is that these 2 molecules need to collide with each other. And if you increase the concentration, you're going to have more collisions. Secondly, not every collision is going to lead to a reaction to take place. Because there's that activation energy. There needs to be a certain amount of energy associated with those. And when you have a reaction, there's sort of a bell curve of the amount of energy that all the molecules will have. And maybe like only this bit here will have sufficient energy. But the more concentration you have, the more molecules there'll be with sufficient energy. And also, the collision needs to be in the right orientation. The active groups where bonds are going to be, you know, breaking and reforming have to be near each other. So higher concentration means there's more collisions, and more of those collisions will be in the correct orientation. So basically it is just that the higher concentration means that those 3 criteria for a reaction to take place will happen more frequently. But we want you to keep those 3 criteria in mind. And then now we move on to a question about combustion. Is combustion of propane in oxygen an exothermic or an endothermic reaction? Now, Usually you can just think from common sense if you remember what propane is, or watch King of the Hill with propane and propane accessories. It's a hydrocarbon. It's a petroleum product, and we're burning it because we want to gain energy, to heat something up, etc., etc. So it has to be an exothermic reaction. We are lighting it up to generate energy. So we know that combustion of propane is exothermic. And generally also, a combustion reaction is pretty much always going to be an exothermic affair because oxygen is combining with something and releasing a whole bunch of energy in the process. But more than that, we need to write out the balanced chemical equation for the combustion of propane and oxygen. So first, we got to think back to the previous test to know what propane is. So let's write the structure out for a second, so just we know what its chemical equation would be. Prop means that we have 3 carbons, and it's just propane, meaning there's nothing else special about it. So all the other spaces need to be filled up with hydrogen. But the structure is not important for this question, aside from just us knowing what the chemical equation is. So it's C3, H, 1, 2, 3, 4, 5, 6, 7, 8, H8. So that's propane, and it's a combination of propane and oxygen. So there's some amount of O2. And then that's going to react together, and like all these combustion reactions, we need to remember that the products of a complete combustion are carbon dioxide and water. Also, that all of these are going to be in the state of a gas. So, with this, now we need to balance the equation. And the best way to balance an equation is always to find what I call the dependent molecule. For instance, I wouldn't start with trying to figure out how many oxygens to balance, because O2 is here on its own. You know, I can add as much oxygen on this side as I need to justify however many oxygens I end up with on the right-hand side. But over here we have the propane is more complicated. This carbon and the hydrogen are bound together inextricably. So we should start with one of these. And for most, there's sort of a usual standard that I go by when I'm trying to balance equations. I'd start with metals, then nitrogen, carbon, oxygen, and then usually hydrogen is the last one. But in this case, but then the exception is things that are dependently bound. So there's no metals here, there's no nitrogen. So the first thing I'd always do is try to balance the carbon. There's 3 carbon on the reactant side, and only one thing over here has carbon. That's the carbon dioxide. So we would just make 3 carbon dioxide. So now we have 3 carbons on both sides. But now we would want to balance out the rest of this particular molecule. So rather than going to oxygen, I would balance out the hydrogen next. There's 8 hydrogen over here, and the reactants only have water for hydrogen. It's H2, so I would need 4 water molecules to get 8 hydrogen over here. So now we've balanced the carbon, we've balanced the hydrogen, and now we can take a look over here. How many oxygens are on the product side? There's 4 for H2O, and there is 6 for the carbon dioxide, 3 times 2. So there's 10 oxygens total over here, and we need 10 oxygens on the reactant side. So 5O2 here will give you the Rex. So there is the completely balanced equation as a result. And you can always double check and go back and make sure that things are balanced up. But I would always go down this scale to pick the first atom, the first element that you're going to try to balance. Then try to balance any other atoms that are part of that molecule. So I started with carbon, then I go to the next piece of that molecule, which was hydrogen. But ultimately, you can find your own approach to it. Just be careful that you don't get yourself stuck in loops where you're trying to balance oxygen before you've dealt with other things, because then you'll start cycling around over and over again, trying to constantly fix things back and forth. Next, now we have, on the following image, draw an energy diagram showing the relative energies of the reactants, products, and transition states for the combustion of propane and oxygen. And I already drew like a quick sketchy version of this. This is like the energy levels setup. So the first thing we need to keep in mind is that the combustion of propane, as we said in the earlier question, is exothermic. And what that means is that the reactants are at one energy level and that the products will be at a lower energy level. And that energy here is the energy that was released, just as a way to visualize that. But then, of course, there's always that awkward transition state where you've broken a bond and or moved these atoms around, and they're not in an ideal spot. And that's this difference right here. And that is the activation energy, or EA for energy of activation. And so there you go, is the three states. Is you got your reactants, your products, and then there's this transition state, and then the difference between the reactant spot and the product spot is the activation energy. Now, if the question was reversed and it was an endothermic reaction, the activation energy is still higher, but then the activation energy is still going to be a matter of the products, not with that. So endothermic reactions are often very hard to get started because of that. And they're only spontaneous if we have enough entropy. But I'm getting a little bit ahead of myself in that regard. So then we need to explain what characterizes a spontaneous reaction. And for this, then we need to think about the three things that go into a reaction being spontaneous or not. And there's the equation of Gibbs free energy. And I'm not sure how detailed this went in, but we have this number G. And if this number ends up being negative, then we have a spontaneous reaction. And the reaction is the change in enthalpy, or heat, minus the change in entropy times the temperature. So those are the three things that will characterize a spontaneous reaction. Anything that makes the Gibbs free energy more negative. So therefore, it'd be a negative enthalpy, or a release of energy, oh, I'm sorry, I'm getting way ahead of myself. Never, that's not what this question is asking at all. I have in my rush misread the question. What characterizes a spontaneous reaction? So no, I was overthinking the question there for a second. All that this means is a reaction that occurs without the need for continuous energy supplied. So yeah, just now don't get that mixed up with high activation energy. So there's a lot of reactions that just at a certain temperature, they then will spontaneously happen. But a non-spontaneous reaction is one where you have to continually input energy. But a reaction that's spontaneous does not need the continuous energy supply. So yeah, see, I was jumping ahead here. And what I was starting to do was to answer this. What three factors are determining if a reaction will occur spontaneously? And those three factors are the enthalpy, the heat, the entropy, and the temperature. And sorry for that little delay there. But so a negative enthalpy, which means a release in energy, makes it more likely something is spontaneous. An increase in entropy also makes it more likely that something is spontaneous. Temperature will determine if something is spontaneous if there's a mismatch between these two. If you've got a positive enthalpy and a positive entropy, then only at certain temperatures will something become spontaneous. But for now, these are just the three factors: enthalpy, entropy, temperature. And how those factors interplay will determine whether or not something is spontaneous. So now we have number 9. Number 9, which physical state has the greatest entropy? And again, the most important thing to think about entropy is that it's how many different uh, valid configurations of this system can there be? If I have a solid, it's going to be a block, it's just going to sit there as a block and it's not going to do much. The individual molecules in a solid vibrate back and forth, but they don't move around much. If I have a liquid, then all of these molecules can slide around inside, but they're still confined to a specific volume of liquid. If I have a gas, now the gas will fill whatever container you put it in, and it can have every single possible configuration of these different gas particles moving around. So it is a gas that will have the greatest entropy. And I've just sort of explained the reasoning right there. Is gas has the most freedom to move more valid configurations, which represents more entropy. And so, again, bad formatting here, but we have number 10. The process of a solid changing into a liquid was called, and we're not trying anything special, that's just melting. And we ask, does this physical process require energy, or does this process produce energy? And we need to think a little bit. There's different ways you can think about this. You could just memorize the fact that as a state goes to be more and more spread out and increases its entropy, that it requires energy to do that. A solid is at a lower energy state because it's not moving as much as compared to a liquid. So we would know just based on that, it requires energy. If you think about it in terms of the Gibbs free energy equation, we know that increasing would increase entropy. So if it released energy as well, if enthalpy was negative and entropy was positive, then turning into a liquid or a gas would always be spontaneous, and we would see everything vaporize away, and that doesn't happen. So it actually has to oppose each other. So therefore, the enthalpy has to be positive. It does require energy. And so now here we are. Under what conditions will this physical process occur spontaneously? When will we spontaneously see things melt or spontaneously turn into a gas? And then again, that answer is here in the equation. If our enthalpy is positive and our entropy is positive, we need to get the entropy to be worth more than the enthalpy, and that is with the temperature. So we reach a certain critical temperature which makes the entropy more of a factor, and that is the temperature at which things melt. So they have to reach the melting temperature of the chemical. And then we have, which of the following is an endothermic process? And so this is just a matter of, endothermic means that it is absorbing, it is requiring energy. So we could just work on a process of elimination to check. So for evaporation of water, maybe, but not definitely one way or the other, just on the most simplest basis. Burning of wood, producing lots of flame. So that's exothermic, that's releasing lots of energy. So it can't be that. Explosion of dynamite, ooh, lots of energy there. That's exothermic. Discharging a battery. Well, a battery is able to do work. It can turn a light on, something like that. So it's releasing energy to do work somewhere else. So that's definitely exothermic as well. So by process of elimination, evaporation of water it has to be the endothermic process. We can also look at it and say, oh, well, the evaporation of water is a phase change from a liquid to a gas. And if we scroll back up, we remember just from this previous question that any time that you're going to a higher entropy state, it requires energy. So we also know based on that that evaporation of water is endothermic. And then we need that as our reasoning, is that liquid to gas is endothermic. And really that's the main thing is endothermic because it requires energy. Okay, and then we have number 12. Given the choice, would you use a thermosetting plastic or a thermoplastic for manufacturing a kitchen countertop? So there's a little bit of an assumption come in. What is it that we want out of a kitchen countertop? But before that, let's think about what these two things are. A thermosetting plastic is something that's moldable until you let it cool down. Then it sets in place. At that point, it won't reform very easily. A thermoplastic, however, is fairly reversible. You can set it into a certain shape, but then if you heat it back up, it'll remelt. So one of them is formable once and then tends to stay in shape, and then one of them is reversibly set or moldable. Now, when I think about my countertops, I will sometimes, for instance, put a hot dish onto my countertops or throw something else on there. There's a lot of temperature going around in the kitchen. If you can't stand the heat, you got to stay out of the kitchen. So I would not want a countertop that might start turning gooey if it got hot. So I would want a thermoset plastic. It won't deform under high temperature. And that's all there is to it. If you can find some other justification, then you can use that as well. But generally, we would want a thermosetting plastic for areas where you're constantly getting exposed to temperature. And now we have number 13. Explain the reason why low-density polyethylene is less dense than high-density polyethylene. And include a simple diagram in our explanation. And I think, for me, going to the diagram first is helpful. So the thing about low-density polyethylene is that when it's formed, it's less controlled. So you will have a long, straight chain of carbons, but then you'll also have side chains. And so if you imagine another polyethylene that's got these side chains on it like this, you can see that you're going to have a lot of dead space in there as all these side chains are repelling each other. High-density polyethylene is designed more carefully where you don't have those side chains, so you just have a straight line of your carbons. And as a result, another high-density chain can fit real tightly in together like that. So HDP, and so those are the main things. So you need to mention that the HDPT has no side branching. So it can fit together. And in the low density polyethylene, It's harder for it to be as close. So just literally, you'll have lower density because you've got these bits of dead space that exist that don't exist in the high density polyethylene when it's put together. And now we move on to the real meaty polymerization stuff. For the following structures, what kind of polymer is represented? Addition or condensation? And then identify, circle and label it, the bond functionality if applicable. And we're only really looking for two kinds. It's either going to be an amide or an ester condensation reaction. So let's look and see what those look like. So an amide bond is one carbon with a double oxygen on it, and then a nitrogen attached onto it. So that's an amide. And an ester, and then this is part of a larger chain. And so same thing here. An ester is like an amide, but instead of that oxygen, instead of the nitrogen, there's an oxygen. So what we want to do is for each of these polymers, we want to see if we can find this telltale structure of an ester or an amide. And if those exist, then we know it's a condensation reaction. So let's look through here. So starting off, we just see a nitrogen, but it's not quite what we want. But here we go, nitrogen and a carbon with a double oxygen on it. So those that telltale structure of an amide. And therefore we know this is a condensation reaction. And we've already gone and labeled, circled and labeled that bond functionality. So there we go. Then we go to the next one. And again, we start by looking for those telltale structures. We've got something that looks like it might be an ester, but it's just the very edge. So let's look more in the center here. Up, there it is. There is that telltale ester structure, which means this has to be condensation. And then we look at this last one. Okay, well, I don't see any nitrogens. I don't see any oxygens, so it can't be a condensation. So all that's left for this is for it to have been an addition reaction. And there is no functional group to circle when you have an addition reaction. So always my way would be to start by looking for those telltale structures. And then if you can't find those structures, by process of elimination, it's got to be an addition polymerization. Now we're coming at it from the opposite direction. Draw the reaction and the resulting repeating unit to form polymers from the following monomers. Now, from here, there's some other ways we can think about it. So an addition reaction always, in our cases, needs a carbon-carbon double bond, because that double bond is going to get sacrificed to cause the reaction. If we don't have an addition reaction, we might have an amide or an ester reaction. And in that case, we need an amide group and a carboxylic acid group. And for the ester reaction, we need an alcohol group and a carboxylic acid group. So again, what we can do is try to find these telltale signs. So for the first one, there's no oxygen, there's no nitrogen, so it can't be a condensation, and we've got that carbon-carbon double bond. And so to show that reaction, I'll just draw the exact same molecule right next to it. But I've already made a mistake, I can see, because I wasn't being very careful. This carbon actually has a chlorine here instead of a hydrogen. So there we go. And like I said, this double bond will be sacrificed and form a new bond here, and it'll form a bond off with another one conceivably, and lead to, and for the polymer, we always have this little indentation, but then we're just gonna rewrite this with the double bonds removed, because then this one also splits off. So first we have a carbon with a chlorine on it and a hydrogen. Then this is a single bond now, so that's a hydrogen, hydrogen. Then the next one, this one right here, we have another chlorine and a hydrogen, and then a hydrogen, hydrogen, and there we go. So that is the polymer structure and the little reaction. So now we'll do the next one. So I do not see any carbon-carbon double bonds, which means this is probably not an addition reaction. So now we're going to look, and what do we see? We see these telltale groups, don't we? There's the amine group, and here's the carboxylic acid group. So those will combine together to form an amide. So I'm going to delete those boxes, and I'm going to do the exact same thing as I'm just going to draw the exact same structure here. Nitrogen, carbon, and then an R group, and a hydrogen. And so this carboxylic acid will react with this amine group, where this carbon links here, and these will form H2O. And then once again, I'm just going to open this up and just draw the whole structure. So in with a hydrogen. Now bonds here. See, it loses one of the hydrogens at the bonding process. So there's this that's going off. Then this carbon has an R on it and a hydrogen. Then this carbon has that double oxygen and then bonds onto the nitrogen bond over there. And I'm getting a little close there. And so there you go. That's what it forms. A little messy. Let me clean that hydrogen up. There you go. And then we'll look at this last one right here. Again, no hydrogen, no nitrogens, no oxygens. We've got this benzene group, but the benzene does not do anything special. It's just another side chain, as much as the chlorine was from the first one. What we do have is that carbon-carbon double bond. So I'm going to clean this up just because I'm using a little bit too much space here. And again, we're just going to draw the exact same molecule with a hastily drawn benzene ring here, and then these two hydrogens. This double bond breaks like this. This goes off to another one. And that is all she wrote to create this. And then we're just going to draw these out, remembering that the double bonds go away. So the first one is a carbon with two oxygens linking off to something. The next one is the carbon that's got the benzene. Then again, carbon with two hydrogens. I said oxygen a second ago, sorry. And then another one with the benzene ring. And that leads off. And so there we have that nice polymer here. And this is referred to as polystyrene, what we make styrofoam cups out of. So you see, you're getting that practical information when it comes to these polymers. And now we ask, how are proteins held together? And how do they maintain their distinctive shapes? Well, to know this, you need to remember that proteins are made out of amino acids. And the name amino acid lets you know what they kind of look like. But it may be good just to memorize it too. You start off with a base carbon, and then there's something off here. But you say it's amino, so there's an amine group. An amine group is an NH2. And it's an amino acid. So there's also a carboxylic acid on it. And then there's many, many amino acids, and the difference between them is whatever this R side chain is. And then again, we can look, oh, what is that telltale thing? We've got an amino group, we've got a carboxylic acid group, and if we scroll back up here, we look, that is an amide. So proteins are held together. With amide bonds, and their shape is determined by their amino acid side chains. So this R can be over a dozen things. It's I took biochemistry about 4 years ago as a grad student, and I don't remember all the amino acids anymore. I had to memorize them at that point, but there's a bunch of them, and there can be ones with sulfur, ones with extra groups, some that are slightly acidic, and all of those electronic uh, configurations can make all these proteins have unique shapes. But you just got to remember, you see these groups, those are that tells you got an amide group building up, and then those individual side chains will give any protein a unique shape. Now we need to name 3 polymers that are encountered in the human body. Well, we're just talking about one, so a protein is one. And again, I apologize for the formatting. These all got bunched together when I converted this. So a protein is one of the kind of polymers that's encountered in the human body. But anything that is smaller units linking together would be a polymer. So I can think about, like, there's DNA, there's RNA, you've got cellulose, you've got which can form up into fats and triglycerides and things like that. And you could even talk about like starch. That's not something that's that the human body produces, but it is a biopolymer that we break down. And there's also glycogen. Ah, the formatting errors have come. And glycogen is a form of sugars bonded together. It's similar to starch, but it's a way that animals will store sugars in their bodies as well. So there's many great answers that you can give for what the polymers that are encountered in the human body are. And you only need 3 of them, but there's a lot of different examples. So now we have 17, again, bad formatting. What are 2 relatively unique physical properties of water? And so we can just think about the fact that, so if you remember, water is highly polar, and it's got a whole bunch of hydrogen bonding, and it has this unique shape to it. And so there's a lot of unique physical properties that the hydrogen bonding allows. With most of the unique properties all come down to that water has high intermolecular forces. But we want to make specific examples of things that are relatively unique about water. And so there's plenty of ones with the guiding principle that we're thinking about how the high intermolecular forces of water are very useful. So it has a very high melting point, high boiling point. Because like if you look at something like, propane, like what we had earlier, propane is actually larger in terms of raw mass than water, but it's a gas at room temperature, whereas water is a liquid. We have a high melting point, we have a high boiling point, it has good surface tension. What I find the most unique about it is that the ice, is less dense than the liquid. And just as a side moment, that has to do with the fact of that bending of the water molecules. So there is this unique structure, basically, and I don't know the correct crystal structure exactly, but you end up with these dead spaces inside of the solid crystalline structure of water, which is why it becomes less dense when it becomes a solid. Also, in regards to all this, it has a high heat capacity. And then we ask, well, what impacts do these properties have with life on Earth? And basically, just for any of these, you need to muse about how that makes life, easier to live on Earth. So, like, the heat capacity, regulates surface temperature. We actually have this effect pretty strongly because of the Great Lakes. The temperatures here in the winter, we have a lot of snow, but the temperatures here don't get nearly as cold as they could be without all of those lakes regulating the temperature. The lower density allows habitability for lakes. Because if the ice was more dense, then lakes would freeze from the bottom up rather than the top, and there would be this a good chance that the entire lake would freeze solid. But because it freezes from the top, then that ice creates a nice insulation layer and makes it more likely that the body of water will remain mostly liquid. Um, and the high boiling point ensures we have liquid water at our temperature. So just whichever of the two unique properties that you choose, you just need to relate to why, if that property was not as extreme or high as it actually is, that it would make things more difficult for human life. And so there you have it. The next from here, we're just to the next exam example. So we've covered the whole thing, and I'd encourage you to go through these exams yourself as well, just to make sure that you're feeling confident in the style. When you take the test tomorrow, you're going to get similar concepts, but the chemicals may be different. The order of the questions may be different. But as long as you feel comfortable with all of the questions here that I've gone through, then you should be all right for the test. So hopefully this will be helpful for everyone. And I apologize again for how late this in the day this has gone up. But good luck with your exam, and I will wish you a good weekend after you take it.